Hi, and welcome to this course sequence on spacecraft dynamics and control. My name is Hans-Peter Schaub, and I'm a professor at the University of Colorado at Boulder. A little bit about myself quickly. I do research on spacecraft dynamics, including formation flying, relative motion descriptions, but also some exciting work on charged astrodynamics, where we're using electron guns and ion guns to create tractor beams, essentially, to attract or repel spacecraft. I've also been involved on several spacecraft missions, including as the ADCS lead on one of them, and I'm currently involved in a deep space mission doing attitude dynamics control applications. So this topic that you're about to hear about is very near and dear to my heart. What is this class going to cover? There are three main sections. After a brief introductory stuff about vectors and notations and so forth, really the three primary topics are going to be rigid body kinematics, rigid body kinetics, and control. So what does those words actually mean? Kinematics is the description of motion. So that means if you've got a rigid body, which I've got my little foam cube here. Foam is always good when professors throw things around, and especially when we drop them. So what this means is rigid body kinematics. We're describing the orientation. How do we now point a spacecraft to point at a particular star? I need an antenna dish to look down at, point at a Earth location. I'm doing science, I need to scan certain part of the atmosphere. How do we describe such motions? And as with translation, there's an infinity of ways that you can describe your position relative to somebody else. There's a distance and a heading that you can use, like azimuth, elevation, and direction, but you can also use just regular Cartesian coordinates, go this far, east, north, south, up, down, those kinds of coordinates. In attitude, we have an infinity of ways to describe orientations. There's the classical yawing, pitching, and rolling that people are familiar with, but there's many other coordinates that have a lot of benefits. They all have challenges and they all have some benefits, and we're going to go over both pros and cons of these and really show you fundamentally how to describe them. This is going to be now very, very useful, because then we can take attitude descriptions of one object and you have attitude description of another object, and now you need to know the attitude of one relative to another. How do we add, subtract orientations, all these fundamental operators? That's rigid body kinematics. The second section is rigid body kinetics. That means we're now taking into account mass, inertia, forces, and torques acting on a spacecraft. So if a thruster is up here firing and this whole thing starts to pitch and it starts to translate, how do we describe all this stuff mathematically? How do we derive these equations of motion to predict them? How do we solve them numerically? And then we also look at systems that are dual spinners. Sometimes you have spacecraft that have a rigid part and another big rigid part that's spinning. That's a very popular communication satellite design, but also some deep space missions. We'll look at gravity gradient torques. We're looking at a system of spacecraft equipped with multiple rotating wheels, like control room with gyroscopes and reaction wheels and those devices. We'll also look at free spinning motion. In space, most of the time, we're not controlling because we don't have much fuel or energy. So we have to exploit the natural dynamics, and that'll be a big chunk of kinetics as well. What's the naturally tumbling motions? How does this object like to move depending on its shape, geometry, mass distribution? Then the last chunk is control. This is where we take the natural dynamics and go, well, this isn't quite stable. I want it to be pointing here in this direction. And then we add feedback on top of it, where you sense the environment, you sense what's going on, and you go, well, I'm pointing about 3 degrees too low. How do I change my wheel speeds? How do I twist? How do I apply torques? How do I apply thrusters to reorient this and guarantee that it will be stable? I won't overshoot, I won't undershoot. I can specify what the performance is going to be. And in particular in attitude, it's a nonlinear problem. So we'll be dealing with nonlinear control definitions, and we'll be looking at ways to actually define stability for very large departures, not just small oscillations. So that kind of sets this part apart. So we'll be using Lyapunov theory for that. And the expectations here is that you should know basic linear control. Essentially that means you need to know how to define the stability of a spring mass damper system. If you know how to tune the stiffness and the damping to get a particularly critically damped system, you have what I would expect. Everything else will be covered in these lectures. So that's the three main topic areas that we cover here. And the course sequences you're about to see are actually coming from my lectures that I teach here every year at the University of Colorado. So we've taken out some of the things that are very course specific, like talking over homeworks and assignments and different arrangements, and we're getting to the guts of the technical stuff. That's what you'll be seeing. It's kind of edited together over the days, and we'll be adding supplementary material as well. But you're following on pretty much with the exact same material that we do in class, and I've posted a variety of problems that you can solve, and that kind of parallels what we're learning in these lectures. Another thing is textbook. These course sequences are set up and designed where I'm providing you everything here that you need to know from the lectures, from the slides, and so forth. But if you want auxiliary reading, the class that I teach is really based on this textbook here called Analytic Mechanics of Space Systems, and it's a book that's used in many schools. I think over 20 schools now use it for a variety of aspects of spacecraft dynamics, and we do as well. So the material you're seeing is going to touch Chapter 1, focus a lot on Chapter 3, that's the kinematics, 4, the kinetics, and then we jump to Chapter 8, which deals with different nonlinear control solutions. So 3, 4, and 8 are the focus here, and if that's of interest. But that's the quick intro. I really look forward to working with you here. I hope you enjoy this material as much as I do. This is a class that I get a lot of feedback on from students who've graduated, been in industry for a while, worked at NASA, at JPL, and then a few years later I see him again and go, you know, Dr. Schaub, that was a really useful stuff I learned in that class. You know, at the time maybe it was full of details, but now that I'm using it, this is material that I find I'm using all the time. 3D representations and dynamics is not just for spacecraft. This is also used for aircraft, surface vehicles, underwater vehicles, robotics, even computer vision and gaming industry use some of this work on how to describe orientations, computational efficiencies, and so forth. So it's a great fundamental topic. We're going to be applying it to space, which is a fun, exciting application. But what you learn is the fundamentals of how to do rigid body dynamics. Thanks.